astronomers have found an object whose light left almost 12 billion years ago, and it behaves like a star with a black hole for a core. This thing is not normal. Its light started traveling when the universe was only about 1.8 billion years old. That's early in strict, hard numbers, not poetry. Galaxies at that time are supposed to be small, messy, still assembling. Instead, buried in James Webb data, researchers pick out a single compact source that is far too bright and far too weird for its age. They give it a nickname, the Cliff. And if you want to know everything about it, then watch this video till the end and subscribe to the channel. Let's begin. Here's the basic setup. In the deep infrared surveys from JWST, astronomers see lots of faint red sources. They call many of them little red dots. They're compact in the images, they don't show visible structure like spiral arms, and they sit at high redshift, meaning their light has been stretched by cosmic expansion to redder wavelengths. The Cliff is one of those dots on paper, small, red, distant. It should be just another data point. It is not. The first real shock comes when they split its light into a spectrum. Instead of a gentle change with wavelength, like you get from a normal mix of stars in a galaxy, the brightness suddenly drops at a specific point. It's abrupt. It's sharp. That drop is the Balmer break, a feature caused by hydrogen atoms. Normally, it's a modest step. In the Cliff, it's extreme. Measurements show this Balmer break is roughly twice as strong as anything seen at a similar distance. That is not a minor detail. That is a headline result. Now combine that with how bright this object is. For how compact it appears in the data, its luminosity is huge. If you insist on treating it as a normal galaxy made only of stars, the math explodes. You end up with stellar densities far beyond what our simulations produce in the young universe. You'd need to cram an enormous mass of stars into a tiny volume in only 1.8 billion years of cosmic history. That is not just unlikely. It is in direct tension with the way structure forms in standard cosmology. So astronomers try the conservative approach anyway. They feed the spectrum into stellar population models and tell them, assume this is all starlight, fit it. The models want an old, massive, very compact population of stars. The strong Balmer break pushes them towards stars that have had time to age. But that's the core problem. There isn't enough time. At this redshift, the universe hasn't had billions of years to calmly build a big, dense, mature core. You're asking for a system that looks like it has a long history in a universe that is still young. Then, the spectrum reveals more. The Cliff shows broad hydrogen emission lines like H-alpha, with velocities around 1,500 kilometers per second. That means gas is moving in a deep gravitational potential, not just drifting around in a quiet star cluster. You also see helium, but the usual signatures of heavy elements, oxygen, nitrogen, and other metals, are weak or absent. That implies the gas is low metallicity, closer to primordial composition. Primitive gas plus extreme velocities plus huge luminosity is a very specific combination. Put all of that together, strong Balmer break, broad hydrogen lines, low metals, compact size, high luminosity. If you keep calling it a simple stellar population, you have to bend your models until they almost snap. The object starts to look less like a bundle of stars and more like a massive gas envelope whose light has been processed and filtered by dense hydrogen. That is the turning point. The data are pushing you toward a picture where you are not seeing a clean galaxy disk or a naked accretion disk. You are seeing an atmosphere, a thick, star-like atmosphere made of gas that is dense enough to carve out that huge Balmer break and hide whatever is at the center. The star you think you see is just the outer layer of a much more dangerous object. So what sits in the middle? Here is where the interpretation becomes aggressive. Astronomers don't just shrug and say, "weird galaxy." They reach for a theoretical object that has been discussed for almost 2 decades, but never clearly observed. A quasi-star, or black hole star. Not a normal star orbiting a black hole, but a configuration where the black hole is the core and a gigantic gas envelope is the star. In that scenario, the power source is not nuclear fusion. It is accretion. Gas falls onto the central black hole. As it falls inward, gravitational energy is converted into radiation. That radiation pushes back on the envelope and holds it up against collapse, just like fusion pressure does in a normal star. The envelope settles into a kind of balance, gravity pulling in, radiation pushing out. Its surface temperature sits at a few thousand Kelvin, which makes it look red and star-like. From far away, it can mimic the spectrum of a cold stellar population. Up close, it is a black hole growth engine. This model naturally gives you several pieces of the puzzle. Huge luminosity from a compact region, because accreting black holes are very efficient at making light. Strong Balmer features and dense gas, because the envelope is thick and hydrogen-dominated. Weak metal lines, because these things should form out of relatively pristine gas in the early universe. And extreme velocities, because matter close to the black hole orbits and falls in very fast. When researchers compare the cliff to these predictions, the match is uncomfortable in a very serious way. It is not perfect, and no one claims this is 100% proven. But many of the most disturbing properties fall into place if you admit one bold sentence. This is a black hole star. A star with a black hole for a heart. Caught in the act of rapid growth less than 2 billion years after the Big Bang. If that statement is even close to true, the consequences are huge. It means the early universe was not just quietly building small galaxies and slowly growing black holes. It was also running extreme experiments in gravity, building temporary objects designed to pump mass into black holes as fast as physics allows. And here's the key escalation. You don't discover something like this by accident with a backyard telescope. You need a very specific machine, tuned to see the faint, red, stretched light from the early universe, and powerful enough to expose the details in that spectrum. That machine is the James Webb Space Telescope, and the same system that revealed the cliff is now scanning for more. So the obvious next question is this: what kind of time machine do you have to build, and how far do you have to push it, before the universe starts throwing objects like black hole stars in your face? A $10 billion machine is sitting 1.5 million kilometers from Earth, and it just forced us to admit we might be seeing a star powered by a black hole. To understand a black hole star, you have to understand the thing that exposed it. James Webb Space Telescope is not a prettier Hubble. It's a 6.5-meter infrared observatory, a huge gold-plated mirror unfolded in deep space at a point called L2, locked there to stare into the cold, stretched light from the early universe. That's the regime where the cliff lives. Without Webb, the cliff is invisible. It's not a poetic statement. It's a hard technical fact. Why park this thing at L2? Because L2, the second Lagrange point, is a gravitational sweet spot. Earth and the Sun's gravity balance out just right so Webb can orbit that point, keep the Sun, Earth, and Moon all on the same side, and use a giant sun shield to stay cold. infrared telescopes need cold. Any heat from the telescope itself would drown out the faint signals from distant galaxies. Webb has to be quiet, frozen, and brutal in what it looks at. That's how you reach objects whose light has been traveling for more than 11 billion years. So why infrared? Why not just build a bigger Hubble and stay with visible light? Because the universe is expanding. Light from galaxies and black holes that formed billions of years ago gets stretched as space itself expands. Short wavelengths get stretched into longer ones. Blue becomes red. Red becomes infrared. By the time that ancient light reaches us, the most extreme, earliest objects have been shifted right out of Hubble's range. They are simply too red. Hubble can't grab them. Webb can. Webb was built specifically to catch the oldest, reddest photons that have been dragged across the spectrum by cosmic expansion. That's why people call Webb a time machine, not as a metaphor, but as a precise description. The farther out you look, the longer the light has been traveling. When Webb detects a source like the cliff at redshift around 3.5, you are not seeing it as it is now. You are seeing it as it was when the universe was only about 1.8 billion years old. You are reading an old frame in the cosmic movie. So how do you go hunting for something as strange as a black hole star in that chaos? You don't start with a perfect model. You start by telling Webb, "Show us everything that looks wrong." That's the logic behind a program with a deliberately loaded name. RUBIES. It stands for Red Unknowns, Bright Infrared Extragalactic Survey. No romance, just a direct mission statement. Go deep into a patch of sky, look for bright, compact red objects at high redshift, and flag anything that doesn't fit normal galaxy templates. RUBIES is not expecting comfort. It is designed to drag weird stuff to the surface. Inside that dataset, the cliff shows up as one object among many red sources. But here's the key. RUBIES isn't just taking pretty images. It's building a catalogue of targets that are too bright, too compact, too red for the era they live in. These are the universe breaker candidates, the objects that, if interpreted naively, make our models of galaxy formation look wrong, or at least incomplete. The cliff is one of those, but it quickly becomes the one with the most extreme Balmer break, the cleanest signal that something very non-standard is going on. The first instrument that sees these little red dots is NIRC-AM, Webb's near-infrared camera. NIRC-AM does the basic job: take deep images in multiple infrared filters and map out the field. When you look at those images, the little red dots are just that: tiny, unresolved specks. No spiral structure, no visible arms, no neat disks, just compact red points that, at those distances, should not be that bright and that numerous. NIRCam can tell you where they are, how bright they are in each filter, and how small they look on the sky. Already, that is enough to make theorists nervous, because the implied sizes and luminosities are pushing the limits. But images alone don't tell you what the light is made of. To know what's really happening, you need to break that light apart and interrogate it. That's where NIRSpec comes in. The near-infrared spectrograph is Webb's interrogation tool. Instead of taking a picture, it takes the light from an object and spreads it into a spectrum, a barcode of brightness versus wavelength. From that barcode, you can read out redshift, line strengths, gas velocities, chemical composition, and more. MIRI, the mid-infrared instrument, pushes into even longer wavelengths, giving extra leverage on dust and cooler components. When NIRSpec and MIRI are turned on the little red dots, the game changes. For many of them, The spectra show sharp breaks instead of gentle slopes. They show broad emission lines, especially hydrogen, with velocities of thousands of kilometers per second. In some cases, metal lines are present and strong, marking active black holes in more standard configurations. In others, like the cliff, key metal lines are weak or missing, while the Balmer break is extreme and the hydrogen lines are broad. That combination is not what you expect from a normal galaxy full of stars. Normal stellar populations give you smoother spectra. Normal active galactic nuclei, standard quasars, show high ionization metal lines, hard X-ray signatures, and continuum shapes that don't line up with what you see here. The missing fingerprints are as important as the features that are present. When the data show that the usual lines are gone or suppressed, the message is clear. This is not just a bunch of stars arranged in some exotic way. So Webb, through NIRCam, NeoSpec, and MIRI, isn't just imaging the early universe. It is actively breaking our old categories. It hands you objects that look like galaxies in images, but confess, under spectral interrogation, that they are something else entirely. That is how you get driven, step by step, toward the idea of black hole stars. The telescope's design, its placement at L2, its infrared sensitivity, its survey strategy. Every piece of that engineering is what allows a thing like the cliff to be dragged out of the noise. And here's the unsettling part. If one quasi-star candidate can hide in a single RUBIES field, what else is buried in the rest of Webb's datasets, waiting for someone to notice that one spectrum, one break, one broad line that doesn't belong? Because the cliff is not alone. It's just the most extreme case. To see how bad the situation is, you have to zoom out and look at the entire population of these little red dots. The swarm of compact, overpowered specks that might be rewriting how we think the early universe built its first monsters. In the James Webb data, there is an entire class of objects that make the early universe look older than it has any right to be. Astronomers call them little red dots. Off the record, before the papers, a lot of people called them something harsher, universe breakers. Because when you first plot their properties, they don't just look inconvenient. They look like they are punching a hole straight through the timeline you were taught. Here's the basic problem. These little red dots often show up at redshifts around 7, 8, 9, even 10, and beyond. That means their light left when the universe was within the first 700 million years after the Big Bang. That's a hard number. Under standard models, this is a phase where galaxies should be small, chaotic, still building their first serious stellar mass. Not clean, not settled, definitely not looking like massive mature systems. But when you interpret the light from many of these dots as if it comes from normal stars, you get something that feels wrong immediately. Their colors come out red and old looking. The models tell you, this looks like a mature, evolved stellar population. The kind of thing you expect in galaxies that have had billions of years to form, merge, and age. Except at redshift 7 or 8, you simply do not have billions of years to play with. The clock doesn't allow it. So either the models are misreading the light, or the universe built heavy, red, seemingly old stellar populations in a tiny fraction of the time you expected. Both options are serious. Neither is comfortable. Then you add mass and size to the story. Early analyses of these little red dots suggested some of them might hold billions of solar masses worth of stars packed into regions smaller than many galaxies you see around us today. Billions of suns worth of mass, crammed into a compact volume, appearing less than 1 billion years after the Big Bang. You are not tweaking around the edges. You are talking about densities that make people who run simulations start double-checking everything, because their code rarely produces such monsters that early. Look at what that means physically. You're saying that in the time it took the universe to go from hot plasma to first real galaxies, some regions managed to slam together enough gas, form enough stars, and assemble enough structure to rival or exceed the cores of massive galaxies we see nearby, but in 1/10 of the time. That is not a small adjustment. That is a direct challenge to the standard growth timeline. So the community did what it always has to do in this situation. Lay out the least insane options and see which one survives. For the little red dots as a population, 2 main explanations rose to the top. Option 1. Tiny, ultra-dense galaxies in a hyperstarburst phase. In this picture, you have compact galaxies going through extreme star formation episodes. They are churning out stars at ridiculous rates, burning through their gas. Fast, appearing redder either because of dust or because they have a weird mix of young and slightly older stars. You keep everything powered by star formation. No exotic engines, just galaxies running at settings near the maximum of what you think is possible. Option 2. Galaxies dominated by overmassive black holes. In this scenario, the central black hole is so large relative to the stellar mass that it takes over the system's energy output. The light you see is heavily influenced by accretion onto that black hole. The mass of the black hole is not some small fraction of the total like we see in the local universe. It rivals or even exceeds the stellar mass. The black hole gets a massive head start. The galaxy's stars are lagging behind. Both of these explanations are serious, and neither is easy. Hyperstarburst galaxies at those redshifts require star formation rates that are extremely high and sustained in small regions. You need to move gas in fast, compress it, and convert it into stars with brutal efficiency. Overmassive black holes, on the other hand, mean you have to grow black holes very quickly from some kind of seed. You need feeding rates close to or above the usual safe limits for long periods. Then, you try to put these options into simulations. That's where the phrase universe breaker really earns its name. In most standard cosmological simulations, you can occasionally get something dense, or bright, or fast-growing. But getting large numbers of little red dots with the observed properties is hard. You either have to push star formation physics to extreme, finely tuned limits, or you have to allow black holes to grow in ways that are more aggressive than your usual feedback rules like. So you are stuck. If the little red dots are starburst galaxies, they are some of the most violently efficient star factories in cosmic history. If they are black hole-dominated systems, then black. Holes are getting massive faster than our normal coevolution stories allow. In both cases, you're hitting the edges of what your models can comfortably produce. This is the corner Webb forced cosmology into. You can't ignore these objects. There are too many of them in the deep fields. You can't write them off as data errors. Their signals are strong. So you have to admit that something about your view of early galaxy and black hole growth is incomplete. And remember, all of this is before you even get to the cliff. This is the average crisis. The general population of little red dots already makes the early universe look crowded with compact, overpowered systems. To deal with them, theorists started experimenting with more extreme ideas. More efficient cooling channels, different feedback recipes, early black hole seeds that start heavier, episodes of super Eddington accretion, and so on. The usual knobs turned closer to their limits. But then objects like the cliff show up and say, "That's not enough." Because the cliff doesn't just sit in the uncomfortable region of parameter space, it goes past it. Its Balmer break is stronger. Its combination of compactness, luminosity, gas density, and metallicity is sharper. Where other little red dots can just about be squeezed into starburst or overmassive AGN boxes, the cliff tears the box open. So here's the escalation. If the general population of little red dots already strains your simulations, what do you do with the one that trashes both of your main explanations at the same time? How do you classify an object that looks like a galaxy in images, but whose detailed spectrum matches almost nothing in your existing libraries? That's why the cliff became the focus. It's the cleanest, loudest example of the problem. It's the one that forced people to say the quiet thought out loud. Maybe this is not just a galaxy or an AGN. Maybe this is an entirely different kind of object we only predicted on paper. And that leads to the next move. Stop talking about these things in the abstract and dissect the cliff in detail. What is its exact redshift? How strong is that Balmer break numerically? How broad are the lines? How compact is it really? Because once you drill down into those numbers, you're not just dealing with a universe breaker anymore. You're staring at a specific candidate for a black hole star. So the next logical step is brutal and simple. Take this one red dot and zoom in as far as the data allows. Rip apart its spectrum. Pin down its distance. Measure every line you can. Then ask, with no safety net, what kind of object fits this anatomy? One object in the RUBIES dataset is so extreme that it forces you to pin it down not just in space, but in time, and admit, this is where the universe starts breaking pattern. We take that one red dot and go all in. No averages. No population trends, just the cliff. Spectroscopy nails its redshift at about Z equals 3.55. That's a concrete number. Translate that. The light left when the universe was roughly 1.8 billion years old. Not infant, but nowhere near middle age. Its photons have been traveling for about 11.9 to 12 billion years before they hit Webb's mirrors, and then end up in our detectors and plots. You are seeing a system operating while the universe is still assembling the large-scale structure we now live inside. At that epoch, you expect growing galaxies, young clusters, black holes that are still working their way up the mass ladder. You do not expect something that looks like this, because the spectrum of the cliff does not quietly fit in with the others. It has a feature that dominates everything. The Balmer break turned up to an extreme setting. In a normal high redshift source, the Balmer break is present, sure, but it's modest. You see a step between the light at shorter wavelengths and the light at slightly longer ones. Here, that step turns into a vertical wall. The measured Balmer break in the cliff is about twice as strong as any other high redshift source we've seen so far. That's not a rounding error. That's a red flag. That tells you that something in this object is either blocking, reshaping, or producing light in a way that standard stellar populations do not. Then there are the emission lines. The cliff's spectrum is not just a weird continuum with a big break. It carries broad hydrogen emission, especially in H-alpha. The line widths are around 1,500 kilometers per second. That means the gas is moving extremely fast in a deep gravitational well. That alone screams massive central object. You also see helium. But the usual metal lines that would signal a chemically enriched environment are very weak or absent. So now you have hot, fast gas with a primitive composition. Pause on that. Primitive gas, high velocities, enormous luminosity, and an extreme Balmer break in a universe that is 1.8 billion years old. None of those pieces are shocking alone. All of them together, in one compact source, are. Next, Size. Imaging from NIRC-AM shows the cliff is unresolved or only barely resolved. In practice, that means we can't cleanly see a disk or extended structure. It's extremely compact on the sky. Yet, when you compute its luminosity, it rivals or exceeds galaxies that are visibly much larger in later cosmic times. So per unit area, this thing is a monster. It is incredibly efficient at turning whatever mass is falling into radiation you can see. This is where the word efficient is important. Stars are only so efficient. They convert a small fraction of their mass into energy over long timescales through fusion. Accreting black holes are much more efficient. They can convert a larger fraction of the rest mass energy of infalling material into radiation. When you see an object this compact and this bright, your first question should be, is this really all stars? Or is there an accretion engine hiding in there doing the heavy lifting? When you line up the numbers from the RUBIES survey and related JWST programs, the cliff stands out instantly. Among dozens of little red dots, it is the one with the strongest Balmer break. It's the one where the combination of broad hydrogen, helium, and suppressed metal lines is the clearest. It's the one where the imaging most brutally tells you, tiny on the sky, huge in power. So, if you want a test case that forces your models to either adapt or snap, this is it. RUBIES wasn't designed to find comfortable objects. It was built to dredge up ahead, compact, bright sources, and force the community to deal with them. Even in that deliberately biased sample, the cliff is the outlier of outliers. It is the record holder, the one that defines the edge of the plot. If you draw diagrams of Balmer break strength versus redshift or line width versus luminosity, the cliff sits at the far edge, where the axes start to feel wrong. And the more carefully you look, the worse it gets for the standard story. If you treat the spectrum as pure starlight, you are pushed toward an old, massive, tightly packed stellar population with low metals, sitting in a universe that has not had the time to build that comfortably. If you treat it as a normal active galactic nucleus, you are missing the usual metal lines and getting a Balmer break that is simply too sharp for standard AGN templates. Every familiar label slips. This is why the cliff became the target for the black hole star interpretation. It is not just strange, it is structured strange. The features are not random. They point in a direction: dense hydrogen envelope, primitive composition, extreme luminosity, compact size, vast gas in a deep potential. That is very close to what quasi-star models have been predicting on theory slides for years. But before you accept that, you have to be honest and push the boring explanation as hard as possible. You have to take the cliff, feed its spectrum into your best galaxy models, and see if you can, even by stretching the parameters to the limit, call it a normal compact galaxy or a dusty, buried AGN. You don't get to jump to new object without first watching the standard options fail under pressure. So the next step is brutal in its simplicity. Assume the cliff is nothing special. Assume it's just a galaxy. Force the models to agree. Then watch where the numbers break. Because when they do, that's when the black hole star idea stops being a wild story and starts becoming the only serious way left to pay the energy bill. If the cliff were just a normal galaxy, our simulations would not be in trouble right now. Let's force the boring answer and see how fast it dies. You take the cliff's spectrum. You tell your code, no black hole tricks, no exotic objects. This is just starlight from a compact galaxy. Stellar population models are very good at this game. They can mix young and old stars. different metallicities, different star formation histories. They can reproduce the spectra of almost every kind of galaxy we see nearby. But when you lock them onto the cliff, they start spitting out something that should not exist at 1.8 billion years after the Big Bang. Here's what the models want. To get that insanely strong Balmer break, they want an old stellar population. Not just formed yesterday young stars, but stars that have already aged, moved off the main sequence, and built up the right mix of spectral features. To get the brightness, they want a massive population. To match the tiny size, they want that mass jammed into a very compact region. So the starlight-only solution looks like this. Old, massive, extremely compact galaxy core, sitting in a universe that hasn't had enough time to build it calmly. That is not a small stretch. That is a direct clash with the growth timescales we usually trust. Now look at the density this implies. If you interpret the Balmer break as coming purely from a dense bunch of stars, you need a core with stellar densities beyond anything we see in local space. More extreme than the centers of massive elliptical galaxies, more extreme than the crowded cores of globular clusters. You're talking about packing an absurd number of stars into a volume that small, and doing it early. Structure formation models don't naturally spit out objects like that at Z, approximately 3.5. You can force it in a toy model. You cannot get it easily out of a full cosmological run without special pleading. Then comes the chemistry problem. The cliff's spectrum shows weak or absent metal lines. That screams low metallicity. Low metallicity usually means early, primitive stars. Stars formed from gas that hasn't been recycled many times through supernovae. That fits the idea of something relatively early in cosmic history. But now you have a real tension. Primitive, metal-poor stars and a super-strong Balmer break do not normally appear together with this kind of luminosity. Metal-poor populations tend to affect the shape of the spectrum in ways that make it hard to match both the break strength and the total brightness at the same time. So you try to tune it. You adjust the ages. You adjust the metallicity. You adjust the star formation history. A big early burst, then a fade, or a mix of bursts, or continuous star formation slowing down. Every time, you are trying to satisfy multiple demands at once. Make the Balmer break strong, keep the metals low, keep the luminosity high, keep the size tiny. The models can usually hit one or two of these goals cleanly. Hitting all of them at once requires parameters pushed right to the edge. That's the point where you stop calling it a fit and start calling it contortion. Then there is the size-luminosity paradox. In the real universe, normal galaxies mostly sit on decent relations. Larger galaxies tend to be more luminous, smaller ones less so, with some scatter. The cliff blows through that pattern. For its apparent size, it is ridiculously bright. Or, equivalently, for its brightness, it is ridiculously small. Either way you frame it, you are off the normal relation by a lot. You are not in the scatter. You are an outlier that makes the plot look wrong. The starlight-only interpretation says, fine, then it's an ultra-compact, ultra-luminous, ultra-dense core. But you pay for that statement immediately with everything else. You now have to explain how that many stars formed that fast, cooled that quickly, and ended up with that specific spectral shape in a young universe. You need extreme gas inflows. You need star formation efficiencies near theoretical maximum. You need feedback from supernovae to somehow not blow the whole thing apart. You are stacking unlikely requirements on top of each other. And we still haven't dealt with the fact that the gas is clearly moving fast. Those broad hydrogen lines around 1,500 kilometers per second are not a minor detail. They tell you that some component of the gas is deep in a strong gravitational potential. In a starlight-only picture, you can try to blame that on stellar winds or supernova-driven outflows, but the velocities and line shapes look more like material bound to, or falling into, something very massive and very compact. That's classic accretion zone behavior, not just a crowded star cluster. So summarize the normal galaxy attempt in plain language. To pretend the cliff is just a dense clump of stars you have to accept. A galaxy core older than it should be, more massive than it should be, more compact than anything nearby, with lower metals than you'd expect for that mass, and with gas speeds that hint at a much deeper gravitational well than the stars alone would provide. You can write that down. You can even make a model spectrum that looks similar on a plot. But physically, it is a mess. This is what it means when people say the models choke. It's not that the code crashes, it's that the scenario it demands is physically implausible given everything else we know about how structure forms and evolves. You're not just asking the universe to be a bit more efficient, you're asking it to skip steps. You're asking for a galaxy core that basically jumps to the front of the line. And remember, the whole point of trying this exercise was to give the boring explanation every possible chance. If normal galaxy could survive, astronomers would happily stop here. But every purely stellar model either breaks a key constraint or demands conditions that are so extreme they are effectively a different kind of object in disguise. So you are pushed to a blunt conclusion. Starlight alone is not paying the energy bill. There is an extra power source in the middle. It is compact. It is massive. It is driving the velocities. It is reshaping the spectrum. And it is not fusion in a standard stellar core. Once you accept that, you have opened the door. You have admitted that there is something buried inside the cliff that behaves like an accreting black hole, but is wrapped so thickly in gas that it doesn't look like a normal quasar. That crack in the door is exactly where the black hole star idea walks in. Because quasi-star models were built for exactly this kind of situation. A black hole doing the energy work, hidden inside a massive, star-like envelope that fools you into thinking you're seeing ordinary starlight. But before jumping straight to, it's a quasi-star, case closed, there's another standard suspect you need to interrogate and eliminate. The hidden quasar, the dusty AGN, the buried active. Nucleus, because if the cliff could be explained as just a weird, obscured version of a known AGN, then you don't need a new class of object at all. So the next move is obvious and ruthless. Assume the cliff is an active galactic nucleus wrapped in dust and gas. Compare its spectrum to every AGN template we have. And then ask a simple, hard question. If this is a quasar in disguise, why does it still refuse to look like one? A simple escape hatch is to shrug and say, all right, it's just a quasar hidden in dust. That would be convenient. That would mean we don't need a new kind of object. The problem is, Webb has seen plenty of dusty quasars. The cliff does not behave like one. Let's be precise. An active galactic nucleus, an AGN, is a supermassive black hole that's actively feeding. Gas falls in, heats up in the accretion disk, and blasts out radiation from X-rays down to the infrared. Even when dust and gas try to hide it, AGN usually betray themselves in very specific ways. You see strong high ionization emission lines from metals like carbon, nitrogen, oxygen. You see a continuum shape set by the accretion disk and hot dust. And if you look in X-rays, you normally pick up hard X-ray emission from the immediate environment of the black hole. That's the standard AGN fingerprint. We've had decades to study it. We know the patterns. Now, Look at the cliff. You do not see the usual forest of strong metal lines you'd expect from a typical quasar, even a heavily obscured one. Several key metal lines are weak or outright missing. That alone should make you suspicious. A GN are messy. They live in gas that has been enriched by many generations of star formation. Metals are everywhere. When you hardly see them, you are not dealing with a textbook quasar environment. Then there's the Balmer break. In a standard AGN template, the continuum is shaped by the bright accretion disk and reprocessed emission from dust. You can get slopes, curvature, reddening. What you do not get is a brutally sharp Balmer break like the one in the cliff. The break in the cliff is too strong and too clean. It does not look like a reddened AGN continuum with a bit of starlight mixed in. It looks like something else is doing the shaping. This is where the detailed spectral modeling hits hard. When you try to fit the Balmer break as a feature from an old evolved stellar population, the rest of the spectrum pushes back. The numbers line up better if you treat that break as being carved out by absorption in extremely dense hydrogen gas. Not by a bunch of aging stars, but by an atmosphere of gas so thick that it imprints a huge step in the continuum as light passes through it. Dense hydrogen envelope, not just ancient stars. That's a big clue. That kind of gas configuration is not what you expect from a normal galaxy disk, and not what you usually associate with a standard AGN torus either. A typical AGN torus is dusty and clumpy, but the classic AGN spectrum doesn't give you a Balmer break like this. Here, the gas itself is acting like a star-like atmosphere around a hidden core. Next, the power level. The luminosity of the cliff is not modest. It's high enough that, if you interpret it as being powered by a black hole, you are pushed toward accretion rates at or above the Eddington limit. The Eddington limit is the point where radiation pressure from infalling material pushes back so hard that it should slow further accretion. Most AGN hover around that limit or below. Super Eddington accretion is when the system ignores that balance and keeps shoving mass into the black hole faster than the usual safe limit allows, often because of complicated flows and geometry. The cliff looks like a super Eddington suspect. The luminosity is too big for a small black hole calmly feeding, and the compact size rules out spreading that power over a huge relaxed galaxy with tons of stars doing the work. You are almost forced into a scenario where a black hole is being overfed in a very tight environment, with gas so dense it smothers and reshapes the emerging light into something that, from a distance, pretends to be star-like. So we're now in this position, a powerful central engine, but missing the classic AGN metal line fingerprints. A spectrum dominated by a massive Balmer break that matches dense hydrogen absorption instead of an old stellar population. Broad hydrogen lines indicating deep gravitational potential, low metallicity, and a compact, extremely luminous source. That is not a normal quasar plus dust. You can bend AGN templates, redden them, obscure them, but you don't easily get this combination. The result is a hybrid monster. From one angle, the cliff looks like a dense galaxy core. From another, it looks like an overfed black hole. From another, it looks like a star-like atmosphere dominated by hydrogen. It sits in between categories and refuses to move. Not a plain quasar, not a plain galaxy, not a neat two-component system where you can say, here is the disk, here is the AGN, just add dust. That in-between region is exactly where the black hole star picture lives. Quasi-stars were proposed as objects where a black hole and a star-like envelope are not separate components, but a single configuration. The black hole is the engine. The envelope is the atmosphere. The light you see comes from the envelope heated by accretion energy. The spectrum is star-like, But the physics at the core is pure black hole growth. And when you lay the cliff's properties next to what those quasi-star models predict, the alignment is too strong to ignore. A massive, dense hydrogen envelope, low metallicity, very high luminosity, a central black hole accreting at or above the Eddington rate, an object that, from far away, can trick you into thinking it's just a strange, old stellar population, until you notice the speeds and the missing metals. That's why "it's just a dusty quasar" is not an honest answer anymore. Webb's instruments have already tested that idea. The cliff does not carry the normal AGN signatures. It carries the signatures of something more primitive, more compact, and more extreme. So here's the blunt summary. The galaxy-only explanation collapses. The dusty quasar explanation collapses. What you're left with is a scenario where a black hole is doing the heavy lifting, buried inside a star-like atmosphere that hijacks the spectrum. That is not a minor tweak to existing categories. That is a new regime. And at this point, the words "working hypothesis" start to feel thin. Because we are not just guessing. We are staring at exactly the kind of object theorists predicted in 2006 and then filed under "probably impossible to observe." The quasi-star, the black hole star. So now the story has to step into that territory directly. What are these things? Where did the idea come from? And why does the cliff look so much like one of them brought to life? In 2006, theorists wrote down an object so extreme they assumed no telescope would ever actually catch one. Now the data from the cliff is forcing everyone to pull that file back out and take it seriously. The idea was simple and violent. In the very early universe, under the right conditions, a huge gas cloud could collapse so fast and so deep that the core would form a black hole before the whole thing had time to settle into normal stars. Instead of a regular star with a fusion-burning core, you get a black hole in the middle and a supermassive gas envelope wrapped around it. One object, one structure. They called it a quasi-star, or, more bluntly, a black hole star. The key point is how it shines. A normal star is powered by fusion, hydrogen turning into helium in the core, releasing energy, and that energy pushing back against gravity. In a black hole star, the core is a black hole. Material from the surrounding envelope falls inward. As it spirals in, it heats up and releases gravitational energy as radiation. That radiation flows outward into the envelope. It doesn't come from fusion. It comes from matter, dropping deeper into the gravitational well. But the effect on the envelope is similar. The radiation pressure pushes back. Gravity pulls in. The system finds a balance. Gravity tries to crush the envelope downward. Radiation from accretion pushes upward. When those two forces match, the envelope can sit in a kind of temporary equilibrium, like a star held up by a black hole engine instead of a fusion reactor. The numbers these models produced were not small. The envelope could weigh as much as 1 million solar masses or more. The central black hole might start relatively small, but over the short life of the quasi-star, it could grow to something in the range of 1,000 to 100,000 solar masses. That's 10 to the power of 3 to 10 to the power of 5 times the mass of the Sun. These are not minor seeds. These are serious black hole embryos, perfectly placed to become the cause of the supermassive black holes we see in big galaxies later. And the timescale is brutal. Quasi-stars were predicted to live only a few million years. That's nothing on cosmic scales. A blink, but during that blink, accretion is intense. The black hole eats. The envelope shines. Then, when the envelope can no longer be supported, it disperses, or collapses, leaving behind a black hole that is far heavier than anything you'd get from the death of a single normal star. You've compressed a huge amount of growth into a tiny slice of time. The theorists who developed these models also knew why we hadn't seen them. These objects are expected to exist only in the deep early universe. They form from relatively pristine gas before much metal enrichment. They are huge in radius, but relatively cool on the surface, with temperatures of a few thousand Kelvin. That makes them bright but very red. By the time their light reaches us, cosmic expansion shoves that red light even further into the infrared. Ground-based telescopes and Hubble were simply not designed to pick them out cleanly at the distances where they should live. So for years, quasi-stars lived in papers and talks. They were handy as a possible solution to the "how do black holes get big so fast" problem. But they were also effectively invisible. Without access to deep, high-resolution infrared spectra of the early universe, they were more like controlled speculation than observational targets. Cosmology's myth beasts, mathematically allowed, practically unreachable. Then JWST launched and started doing exactly what it was built for: deep infrared surveys of the early universe. Suddenly, the regime where quasi-stars were supposed to exist was no longer theoretical ground. It was survey space. The same wavelength range and redshift domain that makes little red dots pop out of the background is the regime where black hole stars were predicted to shine. Now look back at the cliff through that lens. What do the quasi-star models say you should see from far away? A very luminous, compact source. A spectrum dominated by a hydrogen-rich envelope. A relatively cool, red continuum shaped by that envelope, not by a bare accretion disk. Strong Balmer features because dense hydrogen gas is doing heavy absorption and re-emission. Low metallicity. Broad hydrogen lines from gas moving under the influence of a massive central object. And an overall color that lands the thing squarely in the little red dot zone. The cliff checks these boxes one after another. Dense gas envelope. The modeling of the Balmer breakpoints directly at extremely dense hydrogen. Strong Balmer break. It's the strongest on record for a high redshift source. Broad hydrogen lines. H alpha at roughly 1,500 kilometers per second is right there. Low metals, the missing and weak metal lines say yes. Huge luminosity from a compact region. The imaging and derived brightness agree. This thing is punching way above its size. Implied massive black hole? The line widths and luminosity make it very hard to avoid that conclusion. This is why people are not mumbling about quasi-stars as a side note. They're putting black hole star in the title and abstract. The match is too close to ignore. The cliff looks like the observational version of what those 2006 papers were describing. Same basic architecture: black hole core, giant hydrogen envelope, accretion-powered luminosity, short lifetime, early universe. Is it perfect? No. Real data never line up with theory like a cartoon. There are uncertainties in the models, uncertainties in the measurements, assumptions baked into both sides. But the direction is clear. The boring explanations have been squeezed until they snap. The standard AGN templates don't fit. And sitting there, waiting, is a class of objects we already predicted, in exactly the part of parameter space where the cliff lives. So now the discussion shifts. The tone changes from maybe to this might actually be the first one. If the cliff is a black hole star, then quasi-stars just jumped from theory to reality, and that has consequences. It means the early universe was manufacturing black hole seeds in a way we have never directly seen before. It means some of those little red dots are not just dense galaxies or buried quasars. They are black hole growth machines wrapped in star-like skins. The obvious next question is tactical and brutal. How do you actually build one of these things from scratch in the real universe? What exact steps do you need to go from a diffuse gas cloud to a black hole star like the Cliff? Because if that process is real, it doesn't just explain one object. It rewrites how we think the first massive black holes were assembled. Here is the 5-step recipe for building a star whose core is a black hole. Step 1. You start with a ridiculous amount of gas, not a little cloud that makes a few stars. A pristine gas cloud in the early universe, weighing in at something like 1 to 10 million times the mass of the Sun. That's 10 to the 6th to 10 to the 7th solar masses of mostly hydrogen and helium. Pristine means almost no heavier elements yet. No metals. That matters. Metals help gas cool and fragment into many small clumps. Without them, the gas has fewer ways to dump its heat, so it stays hotter and more cohesive. Under the right conditions, this cloud doesn't shatter into a normal galaxy full of small stars. It collapses almost directly. Gravity wins faster than fragmentation. Instead of forming hundreds of thousands of tiny stars, it behaves like it wants to form one gigantic object, a proto-superstar, a single, massive, inflowing structure. This is already far from what you see happening in the local universe. This is early universe physics, where the rules are the same, but the initial setup is extreme. Step 2. The collapse outruns normal stellar evolution. In a regular massive star, the core contracts, heats up, ignites fusion, and pushes back. Here, for the most extreme cases, the core keeps collapsing anyway. The inner region of this proto-superstar becomes so dense and hot that it doesn't stabilize as a normal fusion core. It gives up and forms a black hole instead, before the outer layers have time to fully react. There's no classic supernova that unbinds everything. The envelope is simply too massive and too deep in the gravitational potential to get blown away completely. So now you have a black hole sitting inside an enormous, still infalling gas envelope. Step 3. The black hole starts eating. Gas from the surrounding envelope keeps raining down toward the center. As that material falls in, it releases gravitational energy. That energy appears as radiation, light, heat, photons pouring out from the region around the black hole. This radiation doesn't escape freely. It slams into the inner layers of the envelope, heats them, and pushes them outward. The result is that the outer layers puff up into a huge, extended atmosphere with a surface temperature of only a few thousand Kelvin. That's cool compared to an accretion disk right at the black hole, but it's exactly in the right range to look red and star-like in its overall color. So from the outside, what you see is not the raw accretion zone. You see a bloated, star-sized envelope radiating away the energy being generated deeper in. The luminosity can be enormous, comparable to small galaxies, but the apparent temperature is modest. That is the star of the black hole star. It's not powered by fusion in a core. It's powered by accretion energy buried inside. Step 4. The whole structure lives on a knife edge. If the black hole swallows gas too aggressively and releases too much energy, radiation pressure can drive the envelope outward, strip it, and shut off the fuel. If the energy output drops too low, gravity wins, and more of the envelope collapses in, boosting accretion again. The system hovers near a balance point where gravity pulling in and radiation pushing out roughly cancel. This is similar in spirit to the balance in a normal star, but the engine is different. This balance is not eternal. It's unstable and short-lived. The black hole can go into a super Eddington regime, where it effectively breaks the standard maximum steady brightness rule by funneling gas in ways that let it keep feeding despite strong radiation pressure. When that happens, the envelope is constantly being heated, distorted, and driven. The entire object is in a state of controlled crisis. Bright, compact in terms of where the power is coming from, and wrapped in dense gas that controls what the spectrum looks like. That is exactly the kind of brief, extreme phase a telescope like JWST is built to catch. Very bright, very red, and sitting in the early universe where the light is pushed into the infrared. Step 5. The end game is a stripped core. Over a few million years, the envelope loses the fight. Some of the gas is swallowed by the black hole. Some is driven off into surrounding space by radiation and outflows. The huge star-like atmosphere thins out and finally disappears as a coherent structure. What remains is the central black hole, now massively upgraded. Instead of a few tens of solar masses like the remnant of a normal giant star, you are left with an intermediate mass black hole, somewhere around 1,000 to 100,000 solar masses. That remnant is not the final boss. It's the seed. Drop that black hole into a forming galaxy, keep feeding it with gas and mergers, and it can grow into the supermassive black holes we see sitting in the centers of galaxies today. You've compressed a huge amount of early growth into one violent, short-lived phase. This is how black hole stars solve a major timing problem. They give you heavy seeds early, so you don't have to push small black holes to grow absurdly fast for hundreds of millions of years straight. Now connect this blueprint back to the cliff. A massive, primitive gas cloud collapsing early? Check. A compact, bright source with an extreme Balmer break coming from dense hydrogen? Check. Broad hydrogen lines indicating a deep gravitational potential? Check. Luminosity suggesting aggressive, maybe super Eddington accretion? Check. A configuration that by design ends with a serious black hole seed in a young universe? Exactly what we need. So if this is really how objects like the cliff are built, then they're not just curiosities. They are factories for the first big black holes. They are the missing middle step between tiny remnants of dead stars and the billion solar mass black holes we see less than 1 billion years after the Big Bang. And that drops us straight into the central cosmology problem this whole story is really attacking. How did those supermassive black holes get so big so fast? And what happens to our picture of galaxy formation if their growth starts with monsters like this instead of quiet little seeds? Here's the core problem laid out with no drama added. The universe has supermassive black holes that are too big, too early, and the clock doesn't like it. We see black holes with masses around 1 billion suns less than 1 billion years after the Big Bang. That's redshifts above 6, 7, and higher. You look at those quasars and you're basically seeing billion solar mass monsters lighting up a universe that's barely out of its origin phase. Now, try to grow one of those from a normal black hole of, say, 10 solar masses, like the remnant of a big star dying today. You have less than 1 billion years to go from 10 to 10 to the power of 9. If you do the math, that growth path is brutal. You need almost continuous accretion at close to the Eddington limit, basically feeding the black hole at the maximum stable rate allowed by radiation pressure, for hundreds of millions of years. No big gaps, no long starvation periods, no major interruptions from feedback blowing fuel away. It's not impossible on paper, but in realistic environments, it is hard to maintain. Gas gets heated, gas gets blown out, mergers happen, things are messy. Keeping a small black hole on a perfect growth track for that long is asking a lot. That's the timing headache. It's not that black holes can't grow. It's that they have to grow very fast, very early, and stay on the gas supply with unreal discipline. The standard start at 10 solar masses and just eat picture is under enormous pressure from these early quasars. This is where the seed problem becomes decisive. The mass of your initial black hole, the seed, sets how insane your growth requirements are. If your seeds are 10 solar masses, you have a nearly impossible job. If your seeds are 1,000 to 100,000 solar masses, the story changes radically. Now you don't have to climb 9 orders of magnitude in mass. You only need 4 to 6. The Eddington clock relaxes. You don't need perfect, constant maximum accretion for as long. The growth becomes challenging instead of ridiculous. Black hole stars drop right into that gap. The whole point of a quasi-star is to take a collapsing gas cloud and turn it, over a few million years, into a black hole seed in the 10 to the power of 3 to 10 to the power of 5 solar mass range. Not by some magical shortcut, but by running a single, extreme phase of envelope-fed accretion, while the object is still embedded in a massive gas reservoir. It's like doing the first few 100 million years of normal growth in one short, enshrouded event. Now plug that back into the little red dots. If a significant fraction of LRDs are black hole stars or close cousins, dense, gas-wrapped, overfed black holes, then those dots are not just weird galaxies. They're growth factories. Each one is a site where a black hole is being boosted from tiny to serious in a single, violent episode. That means the early universe doesn't have to rely on slow, steady feeding of small seeds. It can use these turbocharged phases to jumpstart the mass. This solves the early growth problem without breaking physics. You don't have to let black holes ignore the Eddington limit for hundreds of millions of years straight. You just need short phases of very efficient, sometimes super Eddington, accretion inside dense envelopes. Exactly what the quasi-star picture gives you. The envelope handles the energy, the radiation gets reprocessed, the surroundings stay optically thick, and the black hole gets to bulk up quickly while still respecting the overall rules. There's another piece here that Webb is poking at: the relationship between black holes and their host galaxies. In the local universe, we see fairly tight correlations between the mass of the central black hole and the properties of the galaxy's bulge. Things like the M-sigma relation. That tells us that, over billions of years, black hole growth and galaxy growth are linked. They co-evolve. That's the standard story. But observations of little red dots hint at something more aggressive at high redshift. In some of these systems, the inferred black hole mass seems large compared to the stellar mass in the host. Overmassive black holes relative to their galaxies. That means the black hole is running ahead of the stars. It's getting big earlier or faster than the galaxy around it. That alone bends the neat coevolution picture. It suggests that, at least for some objects and some epochs, black holes are not politely matching pace with their host. They're leading. Black hole stars provide a direct mechanism for that. In a quasi-star, the black hole's growth is the main event. The star-like envelope is just the fuel reservoir and the mask. The host galaxy, as we'd recognize it later, extended stars, ordered structure, comes after. So, if many early black holes go through a quasi-star phase, it is not surprising that, at high redshift, you find black holes that are too big for their galaxies. The black hole started its growth before the galaxy finished building its stellar mass. So you can draw a simple, dangerous line. Start with a massive, pristine gas cloud. Build a black hole star. Let it live a few million years and die, leaving behind an intermediate mass black hole. Feed that black hole in a forming galaxy. It becomes an early quasar in the first billion years. Continue the process over cosmic time. It ends up as one of the supermassive black holes anchoring galaxies in the present universe. Black hole star. Intermediate mass seed. Early quasar. Present-day giant. The cliff and its cousins are potentially snapshots on that path. If the cliff is a black hole star caught mid-phase, we are looking directly at the step where the seed is being forged. If other LRDs are already more exposed quasars, we are seeing the next stage, where the envelope has thinned and the AGN looks more familiar. The population as a whole could be mapping out, in real data, the sequence that turns early gas clouds into the black holes that now dominate galaxy centers. That's why this isn't just some niche fix. It cuts into the core of cosmology. It changes how we talk about the first billion years. It lets us replace, "we don't really know how they got that big that fast," with a concrete mechanism. The universe briefly built stars with black hole hearts, used them as growth engines, and then moved on. But now there's a bigger structural question hanging over everything. If black holes can get that far ahead, that early, what does that do to the way galaxies form around them? Does the galaxy build the black hole, or does the black hole help build the galaxy? That's the next uncomfortable step. Taking this from "black holes grow first" as a convenient slogan, and asking if some galaxies we see today are literally the aftermath of a black hole star phase at their core. For years the rule was simple: galaxies first, black holes second. Build the city, then drop a heavy object in the middle. Webb is now throwing back data that says, very quietly but very firmly, sometimes the heavy object shows up first. In the standard picture, galaxies and their central black holes grow together. Gas falls into a dark matter halo, forms stars, builds a galaxy. Some of that gas funnels down to the middle, feeds a black hole. As the black hole grows and turns on as an active nucleus, it pushes back with radiation and jets. That feedback heats and kicks gas, slows further star formation, and keeps everything in rough balance. Galaxy mass and black hole mass track each other over time. That's why we see neat correlations between them in the local universe. But the little red dots, and the cliff in particular, are not playing that game. They are pointing to a different ordering, a phase where the black hole gets a brutal head start before a normal-looking galaxy even exists. The cliff doesn't look like a settled galaxy with a central black hole calmly in sync with its stars. It looks like a central engine in search of a proper host. And it's not alone. Other JWST targets, like systems labeled QS01 in early surveys, show signs of massive black holes living in environments that do not yet have the expected amount of stellar mass around them. When you estimate how big the black hole is, and then compare that to how many stars you can account for, the ratios look wrong by local universe standards. The black hole is too big. The galaxy is too light. It's as if the core finished its work early, and the rest of the galaxy has been playing catch-up ever since. That flips the usual narrative. Instead of "the galaxy builds the black hole," you are forced to consider the black hole helps build the galaxy. In a black hole star scenario, that's not just a poetic statement, it's literal. The black hole star stage is all about a central object dumping enormous amounts of energy and momentum into its surroundings, while the galaxy-scale structure is still forming. Think about what a black hole star actually does to its environment. You have a central black hole swallowing gas at extreme rates. The envelope around it is hot, dense, and radiating hard. There are fierce outflows, winds, maybe even jets punching through channels in the gas. All of that energy doesn't vanish. It slams into the surrounding medium. It compresses some regions, blows others out, and stirs turbulence on scales much larger than the envelope itself. In the standard feedback picture, the galaxies, stars, and supernovae inject energy that influences the central black hole's fuel supply. Feedback mostly flows inward. Galaxy first, black hole second. In a black hole star, the direction is reversed. The black hole plus envelope are the main energy source. That feedback is shaping the gas that will later cool and form stars on galaxy scales. The core is sculpting the outskirts, not the other way around. And remember, the black hole star doesn't last long. Theory says a few million years, then it's over. But a few million years of near maximal accretion at the center of a forming halo is a lot. In that time, the object can grow a serious black hole seed and inject a huge amount of radiation and mechanical energy into the halo gas. On cosmic timescales, that's nothing. On local gas dynamics timescales, it can be a decisive, irreversible event. So black hole stars act like flashbangs in structure formation. Short, intense. One burst and the room is different forever. The halo's gas distribution, temperature, and angular momentum all get reorganized. Some gas is driven out to large radii. Some gets compressed into dense clumps that later form stars. Some settles into a disk around the now heavier central black hole. When you come back hundreds of millions of years later, what you call the galaxy is growing inside the altered debris of that event. This leads to a sharp, almost uncomfortable picture. Some galaxies might literally be aftermaths, not just in a vague sense, but in a concrete one. The black hole star forms first at the center of a fresh, massive halo. It lives fast, grows the core, blasts the surroundings, then dies. After that, the halo cools and settles. Gas that wasn't blown out falls back in, but it's now moving in a potential dominated by an already substantial black hole. Stars start to form in that reshaped gas. Clumps merge. A recognizable galaxy body appears, but the central black hole has already done its first major growth spurt in secret. If this is common at high redshift, it changes how we interpret those overmassive black holes we see with Webb. They are not mistakes of galaxy formation. They are signatures that the galaxy's central engine went through a black hole star phase before the bulk of the stellar mass assembled. The coevolution story doesn't die, but it gets a prequel, an era where black holes are temporarily decoupled from their hosts, running ahead of them. There's another consequence here. If black hole stars are frequent in certain mass ranges and environments, they will control which halos can easily form big galaxies later. A halo that experiences an early black hole star might get its gas heated and redistributed in ways that set its future star formation history. Some halos might get their gas blown out so hard they stay faint and star poor, with a heavy black hole lurking inside a weak galaxy. Others might get exactly the right amount of compression to spark intense star formation once the chaos settles. That means the presence, or absence, of a black hole star phase could be one of the hidden variables behind the huge diversity of galaxies we see today. Overgrown bulges, faint dwarfs with suspicious black holes, compact ellipticals, and more. We're not just talking about a rare exotic. We might be talking about a key branch point in galaxy evolution in the first 1 billion or 2 billion years. Zoom back to the cliff. In this framework, the cliff is not just an oddball. It is a live example of that pre-galaxy phase. A central black hole wrapped in its own fuel, blasting away, using up its environment and rearranging the future of its host. Webb is catching it mid-act, in the narrow time window where the envelope still exists, and the galaxy body has not yet fully formed around it. So the stakes are high. If objects like the cliff are really black hole stars, then some galaxies are not the parents of their central black holes. They are the children. The black hole did something violent and short-lived first. The galaxy is what grew up around the remains. That raises an obvious next question, and it's not a gentle one. What does the full life cycle of one of these things actually look like? From the moment the gas cloud starts collapsing, through the bright black hole star phase, to the moment the envelope is gone, and only the seed black hole is left behind. What happens step by step, and what does the universe look like while it's happening? Because if the cliff is caught in the middle of that timeline, we should be able to map the whole arc: birth, peak, decay, and the silent remnant that follows. A black hole star is not just an object. It's a full story arc: birth, peak, decay, and a leftover core that keeps mattering long after the drama is over. Start at birth. Picture the early universe when it's only a few 100 million years old. No big spiral galaxies yet. No rich heavy element chemistry. Just dark matter halos pulling in gas and enormous metal poor clouds forming inside them. In one of those halos, a particularly massive cloud, maybe 1 million to 10 million solar masses of hydrogen and helium, starts to collapse. Because the gas is so primitive and the cooling channels are limited, it doesn't break into thousands of small clumps the way gas does in the modern universe. It stays more coherent. It falls inward as one huge structure. Under the right conditions, this collapse doesn't stall out as a normal supersized star. The center contracts faster than the outer layers can react. Instead of gently turning on fusion and stabilizing, the core keeps going. It becomes unstable and collapses straight into a black hole. No pretty explosion that rips everything apart. The envelope is too massive and too deep in the gravitational potential to get blown away entirely. So now, very early on, you already have the basic setup: a hydrostatic envelope of gas, held up by pressure, with a black hole embryo sitting in the middle. This phase is rare. You need a specific combination of halo mass, gas inflow, metallicity, and angular momentum. Most places in the universe never hit those exact conditions. But the early universe had enough wild, high-density environments that some regions did. Those are the birthplaces of black hole stars. Now jump ahead to Middle Age, the phase we think we're seeing in the cliff. At this point, the central black hole has been feeding for a while. Gas from the enormous envelope has been steadily raining down into the center, releasing gravitational energy as it falls. That energy flows back out into the envelope, heating it and holding it up. The result is an object glowing with luminosities comparable to small galaxies, even though its power source is a single buried black hole. From a distance, at the wavelengths JWST sees, it shows up as a little red dot. But it's not just any dot. Its spectrum carries the signature of a record-breaking Balmer break, far stronger than in any other high redshift source we've seen so far, plus broad hydrogen lines from fast-moving gas and almost no metal lines. That's the combination that makes the cliff stand out. Dense hydrogen envelope, primitive composition, deep gravitational well, huge luminosity. This is the black hole star at peak. This is the cliff phase. The envelope is still massive. The black hole is already substantial, but not done yet. The object is short-lived on cosmic scales, but outrageously bright while it lasts. Webb tags it as a little red dot, but the spectrum reveals the twist. This is probably where the cliff sits in its life cycle. Not newborn, not dying, but in the middle of its most violent, most visible stage. Then, things start to change. Over a few million years, the envelope cannot keep up. Every bit of gas that falls onto the black hole adds to its mass and also pumps out more energy. Some of that energy goes into driving material away. Radiation pressure pushes on the gas. Outflows and winds carry mass off the surface. The envelope shrinks, thins, and loses coherence. It stops, being an enormous, clean, star-like atmosphere, and becomes a more complicated, clumpy, partially stripped environment. As that happens, the object's spectrum should evolve. The extreme Balmer break might weaken. More of the inner engine's light could start leaking out directly. The system would drift from "looks like a weird star" toward "looks like an emerging active galactic nucleus," or "looks like a compact, disturbed galaxy with a bright core." The exact path depends on details of geometry, spin, and inflows. But the key point is, if black hole stars are real, there should be objects at different stages of this transformation already sitting in JWST's data. That's something future Webb observations can actually test. Re-observe the same little red dots after some years. Compare spectra of similar objects at slightly different redshifts and environments. Look for a sequence: extreme Balmer break, low metallicity, envelope-dominated systems at one end, more classic AGN-like spectra, with stronger metal lines and less dramatic breaks at the other. If we can line those up into a convincing evolution track, it stops being a story and starts looking like a real-life cycle. Eventually, you hit endgame. The envelope is gone as a single structure. Some gas has been swallowed by the black hole. Some has been blown out into the host halo. Some has cooled and started forming normal stars around the central region. What remains in the middle is the black hole itself, now much more massive than the tiny embryo that existed at birth. It's an intermediate mass black hole, something in the 10 to the power of 3 to 10 to the power of 5 solar mass range. At this point, the black hole star as an object is dead. There is no longer a huge star-like hydrogen envelope making that extreme Balmer break. If you observed this remnant later, you wouldn't call it a black hole star. You'd call it a black hole in a forming galaxy, or the engine of a compact AGN, or, if it goes quiet, a dark mass that only reveals itself through its gravity. But its origin still matters, because that early envelope phase allowed it to grow much faster than a typical stellar remnant black hole ever could. Now push even further out in time. Billions of years later, we cannot see dead black hole stars directly. Their envelopes are long gone. Their early spectra are gone. But their fossils might still be around as intermediate mass black holes hiding in places that don't quite make sense. A dwarf galaxy with a black hole that's too big for its size. A dense star cluster whose dynamics hint at a heavy object in the middle. A black hole wandering in a halo after being kicked out of its original host. These cosmic fossils are exactly what people are hunting in nearby space. There are candidates for intermediate mass black holes in some globular clusters. There are dwarfs with suspiciously big central black holes. There are off-nuclear X-ray sources that might be wandering remnants. None of these, by themselves, prove a black hole star origin. But if black hole stars were common in the early universe, some of today's strange black holes are almost certainly their descendants. So the biography of the cliff, if the black hole star picture is right, looks like this: rare direct collapse birth, brief but extreme middle age where JWST can see it as a little red dot with an absurd Balmer break, slow erosion of the envelope, quiet transition into an intermediate mass black hole, and then billions of years of evolution where that seed either becomes the core of a full quasar or hides in a smaller system as a fossil. That's a clean narrative. But right now, it's still a narrative. To move from "this makes sense" to "this is real," we need hard tests. We need more cliffs, more spectra, more time, and direct predictions we can try to kill. So the next step is the most ruthless one. Lay out exactly what observations would prove or destroy the black hole star idea, and then see whether the universe cooperates or makes us go back to the drawing board. Right now, black hole star is not a trophy on the shelf. It's a loaded claim sitting in the middle of the table, and the only honest label on it is working hypothesis. So, what does it take to upgrade that from cool idea to this thing is real and we have to rewrite the textbooks? First, you need more than one. One, cliff can be a fluke, a weird alignment of parameters, or even a hidden mistake. The first task is brutal and simple. Find more cliffs. More objects with similarly extreme Balmer breaks, very compact sizes, broad hydrogen lines, weak metals, and the same kind of "this is not a normal galaxy" pattern in their spectra. Surveys like RUBIES, Primer, and other JWST deep programs are now digging through data looking specifically for that combination. A little red dot, strong Balmer break, odd line ratios. If you start to see a population of them, not just one, the case gets stronger fast. The story shifts from strange one-off to new class of object with consistent properties. If you don't find any more even when you look hard, then the cliff might be telling you something, but it probably won't be a whole new category. The universe gets a vote here. Second, you go after time. Static spectra and images are not enough. If a black hole star is accreting aggressively, its output should not be perfectly steady. Accretion flows flicker, change, rearrange. The envelope might thicken or thin. The balance between gravity and radiation isn't perfectly locked. It can wobble. So you use JWST in time domain mode. You come back to the same objects again and again. You take new spectra. You measure brightness changes and line changes. If what you're seeing is just a big, old, stable bundle of stars, it should not vary much on human timescales. If what you're seeing is a compact, accretion-powered engine buried inside gas, you might catch variability, shifts in the strength of the Balmer break, changes in line widths, changes in continuum brightness. Even modest variability would be a big signal that this is not a passive stellar population. Third, you stop relying on infrared alone. A black hole star is not just a pretty red source, it's a multi-wavelength object. You bring in X-rays and radio, a normal active galactic nucleus with a relatively clean view of the accretion disk and corona is a strong X-ray emitter. In a black hole star, that harsh radiation from the innermost regions has to fight its way through a dense, opaque envelope. A lot of it should get absorbed or reprocessed. So a quasi-star candidate might actually look X-ray faint compared to a standard AGN with the same overall luminosity. That's a measurable difference. On the radio side, any jets or outflows can leave signatures. If black hole stars launch jets that punch through parts of the envelope, they might light up the radio in a particular way. Compact, maybe slightly offset from the infrared position, with spectra distinct from ordinary star-forming galaxies. Combine Webb with Chandra, and later Athena, plus big radio arrays, and you start getting a fingerprint that spans the whole spectrum, not just the infrared piece. Fourth, you count. This sounds boring, but it's crucial. If black hole stars are real, they can't just exist. They have to exist in the right numbers. Too many, and they saturate the early universe with massive seeds, making black holes far more common and more massive than we observe. Too few, and they don't solve the seed problem at all. They become a curiosity, not a fix. So you use cosmological simulations and JWST surveys together. Simulators take their best models for halo formation, gas collapse, and quasi-star physics and ask, in a universe like ours, how many of these things should form per unit volume, per unit time? Observers then look at the actual sky area and depth covered by surveys like RUBIES, Primer, Sears, JADES, and others, and ask, how many extreme Balmer break objects did we actually see? If those two numbers can be brought into rough agreement without ridiculous tuning, the hypothesis survives. If they don't, if you need insane formation efficiencies or absurdly rare conditions, then the theory has to be adjusted or thrown out. Finally, you go for smoking gun. Spectral features. The broad brush picture is already in place. Dense hydrogen envelope, strong Balmer break, low metals. But you want details that cannot easily be faked by other models. That means pushing theory hard. Right now, people are running detailed radiative transfer simulations of black hole star atmospheres. They're trying to predict exact line ratios, subtle continuum shapes, the precise slope on either side of the Balmer break, the presence or absence of certain helium and metal lines under different envelope conditions. They're asking very specific questions. If the atmosphere has this density and composition, what does the emergent spectrum look like at JWST wavelengths? How does that differ from a dusty quasar, or from a compact starburst galaxy, in ways that are not trivial to mimic? Those simulations then hand observers a checklist. Look for this line ratio. Look for this shape in the continuum. Look for this combination of Balmer break strength and helium line behavior. Webb's archive is already full of spectra. If black hole stars have a unique spectral barcode, we might already have multiple examples sitting in the data, misclassified or ignored because they didn't fit any known template when they were first reduced. So the proof plan is clear and aggressive. Find more candidates, track them over time, hit them with X-ray and radio follow-up, count them and match the counts to simulations, and hunt for a spectral signature that nothing else can realistically reproduce. If all of those lines of evidence converge, black hole star stops being a risky phrase and becomes a standard entry in the catalogue of cosmic objects. And there's one more twist. As you start scanning JWST data with this mindset, you quickly realize the cliff is not the only weirdo in town. There are other little red dots, and even big red dots with their own extreme properties, some closer to classic AGN, some closer to dense starbursts, some sitting in the same uncomfortable middle ground. So the next step isn't just proving the cliff is a black hole star. It's mapping out the whole zoo of these red, compact, high redshift beasts and asking, which ones are true quasi-stars, which ones are just heavy, buried quasars, and which ones are something else again? Because once you admit one new predator is loose in the early universe, you have to look around and see what else is hunting in the same dark. The cliff is not a lone freak. JWST has caught a whole crowd of red, compact troublemakers that refuse to fit the old script. Once you have a serious candidate for a black hole star on the table, you start looking around and you realize the cliff has company. The sky is full of other little red dots, and even bigger red monsters that share parts of the same pattern. Too bright, too compact, too red, too early, wrapped in dense gas. Not identical twins, but cousins. Variants of the same underlying problem. The universe seems very good at building overpowered cores very fast. Take Kuiper's LRDZ9. This one lives way deeper in time, at a redshift around 9.3. That means its light left when the universe was only a few 100 million years old. This is the era where, in standard models, galaxies are barely getting their act together. Yet Kuiper's LRDZ9 shows up as another little red dot with a Balmer break and broad emission lines. The signals point to a dense gas-enshrouded AGN, a black hole that's already feeding hard, buried in thick gas. It's not as clean a quasi-star candidate as the Cliff, but it's clearly in the same neighborhood of parameter space. Compact, red, heavily obscured, with gas moving at high speeds in a deep potential. So now you have one object, the Cliff, that looks like a black hole star, and another, Kuiper's LRDZ9, that looks like an extreme, dense, early AGN. Different flavors, same basic idea. Central engines buried in gas, lighting up the early universe faster than we expected. That's a pattern, not a coincidence. Then there's RUBIES Blagen 1 and its friends. Some of the little red dots are much more straightforwardly broad-line AGN. You look at their spectra and you see strong Balmer emission, dense gas signatures, and clear AGN-like behavior, but still combined with significant Balmer breaks. They're not as extreme as the Cliff, but they're not boring either. They still sit in that uncomfortable middle ground where dense gas, strong emission lines, and compact sizes all collide. These systems hint at a continuum of states. On one end, you have classic AGN, bright cores, clear metal lines, familiar templates. On the other, you have the Cliff, extreme Balmer break, low metals, dense hydrogen envelope, very weird for a normal AGN. In between, you've got objects like RUBIES Blagen 1, where the AGN character is obvious, but the surrounding gas and spectral breaks are still pushed into unusual territory. That continuum matters. It suggests we are not dealing with a single, isolated new object, but a whole family of configurations where black holes and dense gas envelopes interact in different regimes. And then JWST takes things up a notch with a so-called big red dot, nicknamed BIRD. Unlike the tiny LRDs, BIRD is larger in apparent size and sits later in cosmic time, around 4 billion years after the Big Bang. Here, the central black hole is already supermassive and openly ravenous. The system looks like a full-blown monster, a huge black hole eating at high rates, radiating intensely, and heavily reddened by gas and dust. BIRD might be the kind of object some black hole stars grow into once the envelope phase is over and the environment has scaled up. In that view, a black hole star like the Cliff is the intense, buried growth phase. Later, as gas continues to flow in on larger scales and the structure evolves, you could end up with something more like BIRD, a mature, massive black hole dominating a still-building galaxy. Red, because it's still smothered in gas, but no longer hiding behind a single, star-like envelope. Early quasi-star, then extreme obscured quasar, then eventually the classic bright quasar in a more settled host. One chain, different points along it. While the headline objects get all the attention, the real power comes from statistics. Surveys are now counting how many little red dots exist per unit volume at different redshifts and luminosities. They're building luminosity functions, size distributions, line width distributions. Then they run simulations with and without black hole stars built into the physics and ask a blunt question. Which setup matches the observed number and properties of these dots? The cliff is the poster child, the extreme example you put in slides. Capers, LRDs-E9, RUBIES Blagen-1, Bird, and the rest of the swarm give you the numbers. If the counts of compact, red, weird spectrum objects line up with models that include black hole stars and don't line up with models that leave them out, that's a strong indirect argument that quasi-stars are not just mathematical toys. If the counts can be matched without them, the pressure on the idea increases. And here's the key thing. Little red dot is not a single physical label. It's an observational label. It just means compact, red, bright source at high redshift. There is no reason all of them should be the same beast. In fact, it would be shocking if they were. The universe doesn't usually give you one object type per observational category. It's far more likely that LRDs are a zoo. Some are ultra-dense starbursts, tiny galaxies converting gas into stars at absurd rates, reddened by dust and age effects. Some are obscured AAGN, black holes with more standard accretion disks and torus structures buried in thick gas. Some may be transitional systems, where an envelope-like structure is partially stripped and the AGN is starting to show through. And a fraction, maybe small, maybe not, might be true black hole stars, where the star-like atmosphere is still the main thing, shaping the spectrum, and the central black hole is still in its envelope phase. The challenge now is to separate those populations cleanly. That means going beyond it's red and small and using every tool we have: line ratios, Balmer break strength, variability, multi-wavelength data, environment, number counts. You want to be able to point at a given LRD and say, with confidence, this one is a dense starburst, this one is a buried quasar, this one is almost certainly a quasi-star candidate. Until we do that, the picture stays messy. The cliff stands out as the prime black hole star suspect, but its cousins matter. They define the context. They tell us how common extreme cores are, how varied the states are, and how far we can push normal physics before we really need to invoke quasi-stars. And this is where the tension spikes. Because once you start seeing a whole zoo of compact red high redshift objects, there's a real danger. Maybe we're overfitting one exotic explanation to a messy, mixed population. Maybe some combination of ultra-compact starbursts and dense gas AGN can explain most of what we see. And the cliff is just the worst-behaved edge case in a still normal universe. So the next move has to be ruthless and uncomfortable. Step back and ask, what if we're wrong? What if the cliff is not a black hole star, not a quasi-star, not a new class at all? What are the strongest alternate explanations, and can they survive the full weight of the data? Because if black hole stars are real, they'll survive that attack. And if they aren't, this is exactly how we'll find out. Science does not care how cool black hole star sounds. If there is a more boring explanation that fits the data, that boring explanation wins. So let's attack the idea head on. First alternative. The cliff is just an ultra-compact starburst galaxy. No exotic object, no quasi-star, no black hole wrapped in a fake star. Just a tiny galaxy in absolute overdrive. In this picture, you cram a ridiculous amount of gas into a very small region and convert it into stars at an insane rate. You tune the ages of those stars so you get exactly the right mix. Some older, cooler stars to build a strong Balmer break. Some younger, hotter stars to keep the system bright. You add dust in just the right amount to redden the spectrum without killing the light. With enough adjusting, you can make a starlight-only model that gets close to the cliff's spectrum on paper. Models do struggle here, but they're not dead. If you allow star formation rates that are extreme, if you let the stellar density go past what we see nearby, if you push the parameters hard, you can bend a compact starburst into something that looks a lot like the cliff from a distance. The Balmer break can be mimicked by a carefully timed star formation history. The brightness can be matched by packing in enough stars. You don't have to invoke a black hole star to build a spectrum that sort of fits. The problem is physical plausibility. To make this work, you need star formation that is off the charts, in a region that is absurdly dense, in a very young universe, all while keeping the metallicity low and not blowing the whole thing apart with feedback. That doesn't violate any single law of physics, but it does mean stacking a lot of extreme assumptions on top of each other. So this option is not fully ruled out, but it feels like asking the universe to hit a very narrow bullseye. Second alternative. The cliff is a dense gas AGN, but not a black hole star. No star-like hydrostatic envelope. No quasi-star label. Just a very heavily buried active nucleus sitting in a weird geometry. In this version, you have a normal-ish accretion disk around a black hole, but the surrounding gas and dust form a thick cocoon or torus that is far denser and more extended than in standard AGN. The light from the disk is heavily absorbed and reprocessed by that gas. The continuum gets reshaped. A strong Balmer break appears because of absorption in dense hydrogen. Metal lines might be weak in our line of sight because of geometry, optical depth, or selective absorption. You still get broad hydrogen emission from regions closer in, moving at high speed, but a lot of the usual AGN fingerprints are muted or distorted. You don't need to claim the envelope is a stable, star-like atmosphere. You just say, this is a messy, dense, high redshift AGN with a gas configuration we haven't properly modeled yet. That alone can do a lot of work. Real AGN are diverse. They already show a huge variety of spectra based on orientation, density, and environment. It's not shocking that early universe AGN, fed by rapid inflows of primitive gas, might push into regimes that our current templates don't cover. In that case, the cliff is not a new class of object. It's a member of the AGN family at an extreme end of parameter space. Low metallicity, very high column density, strange line ratios, powerful accretion. You don't have to rewrite the cosmic bestiary. You just have to accept that our library of AGN templates is incomplete, especially at high redshift and low metallicity. Then there's a third source of doubt, the data themselves. High redshift spectroscopy is hard. You are working at the limits of sensitivity. You're correcting for complex instrument response. You're dealing with skylines, noise, and subtle calibration issues. You're fitting models to spectra that are not infinitely clean. Calibration errors can distort continuum shapes. Sky subtraction issues can affect line strengths. Small mistakes in redshift can shift where you think the break is. On the modeling side, assumptions about the initial mass function of stars, the dust properties, and the metal distributions all feed into the inferred ages and masses. Even the quasi-star atmosphere models have their own uncertainties. We don't have a lab where we build these things and measure them directly. So some of the extreme properties of the cliff might soften as the analysis improves. A Balmer break that looks twice as strong as anything else might end up being a bit less dramatic with updated reductions. Line strengths might move. Metallicity estimates might shift. A scenario that looks impossible today might drift into just very unlikely territory tomorrow. That's not a reason to dismiss the black hole star idea. It's a reminder not to lock it in too early. And this is where the real value of the hypothesis shows up. The point of black hole star is not that it has to be true. The point is that it forces better questions. If you say, this is a quasi-star, you are forced to ask, what does dense gas around an early black hole really look like? What line ratios does it produce? How often does super-Eddington accretion actually happen in the early universe? And what does it do to the observable spectrum? How many such objects can you form before you overproduce black holes? What are the exact environmental conditions required to get a direct collapse envelope? Even if you ultimately decide the cliff is just a dense gas AGN or an ultra-compact starburst, those questions don't go away. You still have to understand how gas behaves around early black holes at low metallicity. You still have to push your simulations into regimes they haven't explored properly. You still have to explain why so many compact, overpowered systems show up in JWST data. So there are two ways this can end, and both are interesting. Option 1. Black hole stars are real. The cliff and a subset of little red dots are quasi-stars. The early universe really did build star-like envelopes around black holes and use them as growth engines. In that case, we've just confirmed a new kind of object predicted almost 20 years ago, and we've plugged a major hole in our story of how supermassive black holes formed. Option 2. Black hole stars are not needed. The cliff turns out to be explainable as a dense gas AGN or an ultra-compact starburst once we improve our models and data. In that case, the label black hole star might eventually get retired or demoted. But the process of trying to make it work will have forced us to understand early AGN, starbursts, and direct collapse environments much more deeply. We still win. Either way, one thing is already certain. The early universe playbook we handed to JWST was missing pages. Objects like the cliff, Capers LRDs9, Birdie, and the rest of the red compact zoo have made that obvious. The first billion or 2 billion years are not just a slow ramp-up of small galaxies. They are full of extreme compact engines turning gas into light at rates we underestimated. And that brings us to the bigger perspective you can't dodge anymore. If the universe is capable of building stars with black hole hearts, or even just black holes that run far ahead of their galaxies, then the picture of normal cosmic evolution you grew up with is too tidy. So now we step back from the details and face the bigger, stranger fact. You are living in a universe where objects like the cliff are even possible, where the boundary between star, galaxy, and black hole is not clean, and where the most accurate description of the early cosmos might be much more extreme than we were comfortable admitting. Astronomers are now seriously arguing that some stars might have black holes for hearts. That is not a clickbait line. That is the actual state of the discussion. If the black hole star interpretation holds, then we've just watched a purely theoretical creature step off the page and into real data. Quasi-stars were supposed to be math objects, nice in equations, impossible to see. Now we have the cliff, and a handful of similar suspects that sit right in the gap between star, galaxy, and quasar. Too compact and star-like to be a normal galaxy. Too gas-dominated and primitive to be a standard AGN. Too luminous and extreme to be a boring blob of stars. They occupy this ugly middle zone that basically demands a new entry in the cosmic list. Star with a black hole core. That is a new type of thing. Not a tweak, not a subcategory. a type that literally didn't exist in our observational catalogue a few years ago. If it stands, you will have normal stars, massive stars, neutron stars, black holes, galaxies, quasars, and black hole stars sitting between them, doing a one-time job the universe needed early on and then disappearing as distinct objects. And the only reason we're even having this conversation is because JWST did exactly what it was built to do. The mission was sold with a very simple, very arrogant promise. Show us things we don't even know how to ask about yet. That's what look into the early universe in infrared really means. It means expose regimes where our simulations are weak and our imagination is lazy. Little red dots and the cliff are Webb caching that promise in full. Webb isn't just giving us prettier images, it's throwing back spectra that make theorists admit, on record, we might be seeing quasi-stars, or we might need a new black hole growth channel. This is exactly what a $10 billion time machine is supposed to do. Find the places where our expectations snap. The irony is sharp. At first, the little red dots were universe breakers. Their inferred masses and ages looked like they smashed our neat lambda CDM growth timelines. They made the early universe look too mature, too dense, too efficient. People were half joking that JWST had broken cosmology. Now the same class of objects might end up being universe fixers. Because if a fraction of those dots are black hole stars or quasi-star cousins, they actually solve one of our worst headaches. How did black holes get so big so fast? You stop forcing tiny seeds to grow perfectly for 1 billion years and instead admit the universe ran a few brutal, short-lived hacks, black hole stars, right at the start. So the things that looked like they broke the model might be the exact things that patch the biggest hole in it. That is how real science works. The anomalies are not a nuisance, they're the main plot. Now zoom out one more time and put yourself in the frame. Right now, as you sit here, JWST is still out at L2, cold and silent, collecting infrared photons that left their sources more than 10 billion years ago. Those photons are landing on mirrors and detectors, turning into spectra stored on servers. Most of them haven't even been seriously looked at yet. They're sitting in pipelines, in archives, in half-processed datasets and future survey plans. Somewhere in that data, there might be an object even worse than the cliff, a spectrum with a Balmer break even stronger, a redshift even higher, line shapes even messier, something that makes the cliff look tame in comparison. And some grad student or postdoc or data analyst is going to be the first human to plot that spectrum and say out loud, "What is that?" That's not a hypothetical movie moment. That's literally how this works. Someone scrolls through a catalogue, notices one point that doesn't sit on the line, and refuses to ignore it. And your position in all of this is not trivial. You're watching this story at the exact moment when the idea is still unstable. Black hole star is not a textbook term yet. It's not settled. It's being fought over in papers and seminars right now. You're not reading the final chapter. You're watching a live argument about what counts as real. 10 years from now, either quasi-stars will be standard, boring entries in astronomy lectures, or there'll be a fascinating wrong turn that forced us to sharpen our picture of early AGN and dense starbursts. Here's the real twist. The universe is not a finished book with a fixed table of contents. It's a draft. We keep going back through old chapters, the first billion years, the first black holes, the first galaxies, and scribbling in the margins, crossing out lines, adding new characters. Hubble gave us one version. JWST is giving us a harsher edit. Every time we think we know how stars are supposed to work, we find magnetars or pair instability supernovae or objects right at the edge of collapse. Every time we think we know how black holes should grow, we find early quasars that are too massive, or mergers that are too violent, or now, possibly, black hole stars pretending to be regular starlight. So, yes, star with a black hole heart sounds dramatic, but that's where the evidence is pointing, towards a universe that, very early on, built temporary monsters whose only job was to feed black holes as fast as physics would allow, and then vanish. And the most important part is this: the story is absolutely not done. The datasets are not fully mined. The models are not fully built. Somewhere between the little red dots, the big red dots, and the next batch of spectra, there's probably a result that will make even the black hole star idea look conservative. In other words, the universe is still rewriting its own script. We're just finally building telescopes sharp enough to read the edits. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.